Hey, we're going to revisit integration by partial fractions. Last time we did this, we did it where when we reduced the denominator, we always got linear terms. And that simplified things quite a bit. And we also, all those linear terms were unique. I will provide a link back to that video so you can check that out if you need a refresher. It was a bit ago. But now we're going to talk about two big ideas: repeated factors and nonlinear bases. They're not too bad. It's just a slightly different technique at the start, and then everything follows through from there. So what I'm going to talk about here is that slightly different technique at the start, how to recognize it, what the technique is, and then in a later video, I'll show you guys how to actually solve it all the way through with a couple examples. Okay, so so repeated factors. What I mean by that is that when we take this denominator and we start to factor it out, we will see that we could factor an x squared out, and then inside we'd be left with x plus 3. So the x plus 3 is really nice because that's linear and it's non-repeating. It's that x squared that I'm really talking about at this point. This could also be, x plus 3 squared, and then we would change things up just a little bit. But I'm going over an easier idea. So we could look at this and rewrite this and really say that instead of x squared, it's just x times x. So now you can really see that it's a repeated factor in the denominator. Okay, so the big idea was that we had to we had to break this up um, into A's, B's, and C's. And so when we do that, because of, well, let's take care of the easy part first. I'm going to say that this is our easy part. We know that one of our terms is going to be a over x plus 3. And we're going to have to solve for that a. Now we're going to talk about these double terms. You would think that maybe you could just do like b over x squared or something, and it doesn't work out quite that nicely. What we need to do is we're going to do 1 over x, because it's 1x, and then we're going to do another one over x squared. Okay? If this was x to the third, we would have another term over x cubed, and another one over x to the fourth. And we just keep going and going and going and going. But that's the big idea. So this is a, and these all have to be unique numbers or unique coefficients. So we would do it this way: a, b, and c. Okay. And then as you solve it, you need to find the common denominator and do all that out and come back to that x plus 2. But you just need to break it up into the parts. If this is x cubed, we'd have another one that's at x cubed. If this was x plus 3 squared, we'd have an x plus 3. Then we'd have an x plus 3 squared over here with another term. Okay? So that is repeated factors when they're all linear. Non-linear bases we're going to talk about now. Non-linear bases means that I've factored this out and I've got a nice linear base. This is my linear base, so that's easy. This is my non-linear base right here, right? That's the one that I gotta do something different about. So we do the same thing. Luckily, this is already factored for us. We need to do the same thing we did here. We're gonna say x, so minus 5 over x squared plus 1 x minus 3. This has to be the same as, and I'm going to do the easy one just like I did before, a over x minus 3. That one we shouldn't have to think about too much. This one we got to think about. So it's actually not that bad. What we do is we leave the base alone, just like normal. But our term up here, instead of it just being a constant, it has to be a polynomial that's 1 degree lower than that polynomial. So I'm going to call it bx plus c. So it's a polynomial that is 1 degree lower than that term there. Okay? So let's and then the process would continue from there. I'm going to give you one more example where this is like x to the fourth. So somehow we get to the point, let's make pretend that we have 1 over x to the fourth minus plus 1. We can't factor that. That's not a factorable expression. So what we need to do, and I'm going to get rid of the integral sign so we can just see the arithmetic. I need to write that base. So I'm going to say it's something over x to the fourth plus 1. What goes in the numerator has to be a polynomial 1 degree lower than the 4. So 1 degree lower than the 4 would be a cubic. So I'm going to do ax cubed plus bx squared plus cx plus d. That is a generic cubic that's 1 degree lower than to the fourth, and I've got all my variables in there. So that's how I would set that up. So anytime that it's not reducible, you need to do this thing with the one-term polynomial 1 degree lower. Over here, if you have a repeated base, you just need to repeat it the first time, and then you multiply them together for the second one, and then you multiply it if it was the third, if it was the fourth, if it was the fifth. So I'll send this out, and then I'll have some examples later on. Thanks.